Today's lesson, we're going to look at special functions. One of the essential understandings from this chapter that we want you to be able to do is to determine between linear, which we've looked at functions that are linear before. Those are those straight ones that are constantly increasing. And then these new functions we're going to look at today, step functions, absolute value, constant, and identity functions. And the way we're going to do it is to look at the data, the function itself, or the graph, and be able to distinguish between them. The first example on your sheet shows this postage example, and it says that the cost of postage to mail a letter is a function of the weight of the letter. When you go to mail something, they weigh it at the post office, and then on a stepping scale, they show you or tell you how much it's going to cost. And usually you use stamps, but you can also use other stuff. So over in the table there, you see that the weight in ounces is going to determine it, and it jumps up when you reach the next ounce. So as long as your weight is under 1 ounce or 1 ounce, it would be 39 cents. Anything between 1 all the way to 2 ounces, 63, and so on. And it jumps up once you hit the next ounce. So is this linear? And we would say no, this is not a linear function. The cost is increasing in jumps or steps. And that is not linear. Linear means it's constantly increasing at the same rate. This one jumps to the next one. This is what we would call a step function that we'll look at in a second. Before tomorrow, I want to see if you can answer this next question. Based on that table, what would be the cost to mail a 1.5 ounce letter? We'll check that out tomorrow. All right, so this example we just looked at would be an example of a step function. That's also referred to as the greatest integer function. This symbol right here, f of x equals, and there's double brackets with an x inside, that is the symbol for the greatest integer function. And what it means is the greatest integer less than or equal to x. So every time you have a number, it's the greatest integer, but it has to be less than the number in the brackets. Let's look at an example. The greatest integer of negative 2.4, what would the value of that be? Well, if we look at our table, negative 2.4 is right about there. So what is the biggest integer that is less than negative 2.4? Well, negative 2.4 is between these two integers, or whole numbers. What's the biggest one that's less than that? Well, negative 3 is the greatest integer less than that. Negative 2 is bigger. So if you follow it down, you can see that the y value is negative 3, because that's the integer that the biggest integer that's less than that. And that kind of function continues here. So you keep that same value till you hit the next integer, then you jump up to the next one, and you can see it's a closed-in circle, which means you include the point. When you have open circles like we do here and here, that means you do not count the point. So it's always going to stay the same number till you hit the next integer. Let's do one more example. Let's say we kept going here and we got up to 7.3. What would 7.3 equal? What's the biggest integer that's less than that? Well, the two integers that's between is 7 and 8. The biggest one that's less than 7.3 would be 7. You would stay at 7 until you hit the next integer of 8, and then you jump up to that next value. Let's try an example out. The next problem says the No Leaks RS Plumbing Company charges $60 per hour or any fraction thereof for labor. Complete the table and graph the function where x is the number of hours and c of x is the total labor cost. So if you're going to use this plumbing company, they're going to charge you for that first hour $60. And it's going to stay $60 until you hit the next hour. Once you hit the next hour, then it's going to jump up to the next value. So from 1 to 2, what would it cost? Okay, so what would it cost from 1 all the way till you hit the second hour? Well, the next hour they're going to charge another $60, so now we're up to 120. From 2 hours to 3 hours, now it's going to be up to another 60, so 180, and we kind of continue here all the way through. Another 60 would be 240, and finally the last one here, if you have some fraction of 5 hours, it would be 300. All right, so what does this look like if we graph it out? If you go to your table over here, or if you draw out a little table to make this with the hours on bottom and the cost over here, we can graph it out as a steps function. So from 0 to 1, okay, now notice 0 has the or equals to, so closed in circle. Over to 1, here we have an open circle, because it's not including 1. Then it's going to be $60. Now, once you hit 1 hour, it jumps up to the next price of 120, and right at 2 hours is when it's going to jump up to that amount. So at 1 to 2, it's going to be there, and we keep going. Once you hit 2 hours, now it's going to cost 180. Once you hit 3 hours, now it's going to cost 240. And if we had the rest, we could keep going. And you can see it's a step function. All right, two other ones new functions that we're going to look at, not necessarily new, but we're going to give a name to them, is constant function. Constant function is basically any type of graph where the slope is 0. Any function where the slope is 0, where you're not increasing, you're remaining the same. Here's an example right here. The y-intercept here you can see is 3. It's horizontal. We know that the slope is 0. So it would be y equals 0x plus 3, or we could just write that as y equals 3. Anytime you just got a y equals a number, that's a constant function. Another function that's commonly seen is called the identity function. The identity function is this graph that passes through at 0, so our y-intercept is 0, and our slope, you can see, is up 1 over 1, up 1 over 1. So up 1 over 1. If you have 1 over 1, that's the same as 1 or just x. And plus 0, we're not adding anything. So the identity function is this function y equals x. Another function that they want you to be able to recognize is the absolute value function. Remember, absolute value is the distance from 0. So if we fill in our table over here, plugging in some x's and coming out with our y's, if you put -3 into the absolute value function, that's 3 away from 0, so it would be 3. -2, absolute value of -2 is 2. And going down and filling in our table, we get these numbers. And you can see when you graph that out, -3, 3, -2, 2, you get this V-shaped graph. That is the absolute value function. So anytime you get this V-shaped graph, that is absolute value. The last one we're going to look at today is called a piecewise function. A piecewise function can be used by writing 2 or more inequalities. So if your graph is broken up in pieces where each piece is dependent on the value you're inputting, that's a piecewise function. Let's try this piecewise function out here. This one says we want when x is less than 0, so anytime we're putting in a number less than 0, we're going to use this function. Anytime we put in a number 0 or greater, we're going to use this function. All right, so let's look first. -3. -3 is less than 0. So what we're going to do is put our function in here. So negative 3, we're going to put it into the function negative x. So the opposite of negative 3 would be equal positive 3. Negative 2 is the next number. That's also less than 0. So again, we'll put it into the top function. Opposite of negative 2 would be 2. Similarly, negative 1 would also fall under that and would equal 1. Now we get to our changeover point here. Our changeover point is 0, because once we get to 0, now we're going to go to this graph, because 0 is equal to 0. So at 0, you just input your number into the function x. So f at 0 would equal 0. F at 1 would equal 1. So that looks like just the identity function. Well, if we graph these points out, we get this graph, which is the absolute value graph. So the absolute value graph is really this piecewise function right here. Let's try a couple other examples on your sheet. So now they're asking us to do a few examples here and come up with a graph for some indicated ones. This first one, number 2, is an absolute value graph. When you're doing these problems, your best bet is to probably come up with a table and input some values. So let's make a table, and let's just pick some numbers here to put in for x. When you're making a table, make up some numbers for x, come up with the y values. So now we want to plug these in and see what do we get out when we plug these numbers in. Let's plug negative 3 in and see what we get. So f at negative 3 equals the absolute value of negative 3 plus 1 plus 2. Well, this is going to equal negative 2. Absolute value of negative 2 is 2. 2 plus 2 is 4. So the value here would be 4. And then you keep going. The next one they want us to do is negative 2. So let's see what we get there. When we put negative 2 in, negative 2 plus 1 is going to equal negative 1. Absolute value of negative 1 is positive 1, plus 2 is 3. And then you keep going, plug in the next numbers in. If you put negative 1 in, negative 1 plus 1 is going to be 0. Absolute value of 0 is 0 plus 2 is 2. If you put 0 in, absolute value of 0 plus 1, that's absolute value 1. Absolute value of 1 is 1. 1 plus 2 is 3. If you put 1 in, you're going to get 4. If you put 2 in, you're going to get 5, 3, 6, and you can kind of see a pattern happening. Let's graph those out and see what it looks like. So if we go over here to the graph now and plot them out, negative 3, 4 is right there, negative 2, 3, negative 1, 2, 0, 3, 1, 4, and you can see we get an absolute value graph. Another way we could look at graphing this one too is also using some things we know about functions. One of them is that whatever inside the absolute value sign with x shifts the vertex to the left or right, and it's always opposite when it's inside the function. So if the number's positive plus, it shifts to the left. If it's negative, it shifts to the right. Okay, so the number in here is plus 1. That means it's going to shift our graph from the origin left 1 space. Okay, another thing that we know about functions is the number outside the absolute value being added or subtracted moves the vertex up and down. And this is how you normally do it: up if it's positive, down if it's negative. So here, our plus 2 would shift our function up 2 from the origin. So let's see if that is what actually happened. Here's the origin. We shift left 1 and up 2, yep, and there is our vertex of our absolute value function. We'll talk some more about some of the other examples.